Hello. You should see the desktop now, and you should be able to hear me. Um, does everything seem okay?
Yep.
Yep. Okay, great. Okay, so today we're going to leave the code from trees, and we're going to start talking about grammars. I mean, this is why we were doing trees. The real topic we want to talk about, which is actually the first topic in the textbook, is about grammars. But we're going to see in a minute, trees come up naturally when you start talking about grammars. So it's good for us to spend time talking about the tree data structure because we're going to really need it a lot. Okay. So our goal right now is to describe how we describe programming languages. The idea is that how do you know what you're allowed to type in a Java program? How do you know what you're allowed to type in an SQL program? How do you know what you're allowed to type in a JavaScript program? We want to be able to describe precisely what a programming language looks like. Okay. So a grammar, now grammar is a word that comes from English. The English language has a grammar. And the notion of a programming language have a grammar is closely related to it. But we'll see that programming languages have a grammar that's called a context-free grammar. Languages like English have grammars that are called context-sensitive grammars. And the grammars for languages like English are way more complicated than the grammars for programming languages. Programming languages are baby languages. That's what's technically meant by this idea of a context-free language. They're baby languages. And the languages the humans speak are called natural languages. They're technically called context-sensitive languages. And we won't really go into the difference between them. We're just going to talk about what a context-free language is, what a programming language is. Okay? And then, like in the course CS 410, the course on automata theory, that's where we spell out the real technical differences between these different kinds of languages. Right now, our goal is to just describe a programming language, so a way of describing these things that are called context-free languages. Okay. Okay. Now, what I'm going to do is I'm going to look at some examples. There's the textbook describes this stuff pretty well, and they have this summary of the chapter. I'm going to use it there's some nice examples in the summary, so I want to show you some. Just use this as a way to talk about the ideas. And the main tool for describing a grammar is things that look like this. This is a grammar. The right half of this page here is a grammar. So what we really have to do is we're learning a language for describing languages. So it's famously referred to as, grammars are referred to as a language for describing languages. So it's its own programming language that lets you program the syntax of programming languages. Yeah, and what does that mean? You know, if let me just show you like a real simple idea of what I mean. In a programming language, you can write for int I equals 0, I less than 10, I plus plus. Okay, now you know what that means. You've been taught to read that, and you've been taught to give a meaning to that. Okay, and somebody chose the fact that this would be the word for I. You read this for I from 0 to 10. I mean, you could have just as easily called this loop. And some of the older program languages, they didn't use the word for, they used the word loop. You're looping. Okay, but we have a language, and you're taught the rules for the language. You have this way of building sentences in the language, and you learn how to read those sentences. Okay, a grammar is a language for describing languages. It's a way of writing something like this is a statement in the grammar language that tells me something about the English language. And what this statement says is that a sentence is a noun phrase followed by a verb followed by a noun phrase. That's how I read that. A sentence is noun phrase followed by verb followed by noun phrase. So that's how you, the angle brackets mean that you're describing a piece of the language. And then in between the angle brackets is some sort of symbol that represents the name of that piece. In this case, you think of this as sentence. A sentence is, okay? So just like this language over here has punctuation, like parentheses means the beginning of the conditions in a loop. The semicolon is a punctuation that separates the parts of the loop. The brace is the thing that starts the body of the loop. Okay, here, this symbol means this is an assignment statement. This guy means that. The juxtaposition here, the fact that these are next to each other, means concatenation. It means that whatever this thing represents, it gets followed by whatever this thing represents, which gets followed by whatever this thing represents. And what goes in between the angle brackets is a name, some kind of symbol that you think would help people understand what you're talking about. It wouldn't change this grammar describes some kind of language. It actually describes not English, it describes a little piece of English. I wouldn't be changing the grammar if I changed this to Bob and this to Jane and this to Alice and this to Jane. It would still say that a Bob is a Jane followed by an Alice followed by a Jane. That wouldn't change the meaning of it. It would just become harder to read. But it's much easier to read to think a sentence is a noun phrase followed by a verb by a noun phrase. Okay, what's a noun phrase? You go down here, and it's just like functions defining what when you read a program, if I say down here, f of, and you want to know what that does, you go look up what f means. F is some function. So somewhere in the program would be the definition of the f function. So here, this is essentially naming. This is a name of something. These things that we're naming are called productions. That line of the grammar is called a production. Its name of a production is S. This production, we say, expands into three productions: the NP production, the V production, and the NP production. Okay, what is the NP production? Well, we look farther down the page until we find it. We look for it. They could be in any order. Okay, here we find the NP production. The NP production expands is a followed by an N. You're thinking this is meaning adjective, and this is noun. So a noun phrase is an adjective followed by noun. So writing these production names next to each other means concatenation. So whatever A means, that followed by whatever N means. Well, what's an A? Go down here. Down here, A is, now see how they changed the typeface here? This is a literal. That's like saying int x equal 5. That's different than writing int y equal z. What's y equal to? Well, I have to go look up what z is. What's x equal to? Well, that's a literal. X is 5. I stop there. I don't have to go look up what 5 is. So what is A? A is literally the letter A or the letters THE. Okay. Actually, A stood for article. A noun phrase is article. I thought it was adjective. I was thinking adjective, but that doesn't make sense. A noun phrase is an article followed by a noun. Okay, so an article is the letter A or the string THE. You read this as or. An adjective expands to or is, and then you pick either A or THE. Okay, What's an N? A noun in this baby language, a noun is either the word dog or the word cat or the word rat. Okay. Okay. And then what's V? A V is either the literal loves or the literal hates or the literal eats. Okay. Now, what this describes is an infinite number of, well, actually, this one isn't going to be quite an infinite number. This describes a bunch of different sentences. Okay. This describes sentences. And here's how I would do it. Here's how I can get sentences out of this grammar. A sentence, I'm going to use a different arrow now. I'm going to use this kind of a funny arrow saying that a sentence becomes or expands to, well, I don't have any choice. A sentence expands to a noun phrase followed by a verb followed by a noun phrase. Okay. But that expands, oh, I'm going to put that on a different line. Now I expand or replace or substitute what a noun phrase is. Well, a noun phrase is either it's a followed by an N. And I'm still followed by a V followed by a NP. Notice I've expanded one of these guys. I expanded this thing into this thing. Okay. Now let's see. Let me do another expansion. What is A? Well, A is, I have a choice. I'm going to choose the. And I still have, then there's a noun phrase, a noun, a verb, or a noun phrase. Okay. I'm going to expand something else. Okay. I have the. What is this? An N is either cat, dog, or rat. I'll pick cat. Now I'll put a space in. Notice that the grammar doesn't say to put a space between these. And these grammars can be a little bit sloppy. Okay. In the case of here, I really better put a space between there, because if I do that, I'm actually following the rules of the grammar, but that's not going to be readable. There's actually nothing in this grammar that says I should put a space between the and cat. The space, if you think there's a space between these two, it's not meaningful. This says noun phrase followed by verb followed by noun phrase. It doesn't say in this grammar that you should put a space between them. Okay. But I better to make it readable. So I'm going to put the space. If I made this grammar a little bit more complicated, I could actually put into it a rule that says you better put spaces between these things here. Okay. So to keep things a little bit simple in an introductory way, he made the grammar, actually it's missing something. It's missing something that says there really should be spaces here. Like up here, notice that some places the spaces don't need to be there. But that space better be there. None of those other spaces mattered, but that one does. The grammar for Java makes precise the fact that that space needs to be there, because otherwise you have the variable int I, which doesn't have any meaning. But none of those other spaces have to be there. You can glom all those things together without, and Java will figure that out. Variable name, variable name, an equal sign, the number 0, semicolon, a variable I, strictly less than, the integer 10, that'll be treated as the integer 10, semicolon, the variable I with the plus plus operator. Okay, Java will figure all that out, but you really can't do that. You need that there. And the grammar for the Java language will be very precise about how that space needs to be there, but the other spaces didn't need to be there. Okay, so down here, when I expand this one here to make it make sense, I'll put the space there myself. So N, I have a choice, dog, cat, or rat, and I chose cat. Okay, now I'm going to expand. Oh, but then I still have the, notice I'm only expanding one thing at a time. What I'm doing is called a derivation. Okay, what I'm doing here is called a, and the tradition when you do derivations is you start with your, what's called the start symbol. This S here can be thought of as sentence, but it can also be thought of as start symbol. The start symbol is the top production in there's no ordering to these lines except the first one. The first production is the start production. All the other productions can be in any order you want. The order of these doesn't matter, but the fact that this one came first matters. Okay, so I'm going to do a derivation. I start with this symbol and start expanding it using the grammar. So and you always expand one symbol at a time. I expanded S and got 3 symbols. And actually what I'm doing is what's called a left derivation, because I then continue to expand the thing on the left. I always expand only one thing at a time, and I always expand the thing on the left. And that's technically called a left derivation. So I expanded noun phrase and got these 2 things. Then I expanded the A and got this one thing. Then I expanded the N and got cat and put a space between it. And I'm still okay, so I'm going to keep expanding. I've got the cat. Now a V, I have choice. I can say eats. I'm going to choose eats. And I put the space in there just to make this readable. The language doesn't tell me to put a space in there, but I better, otherwise it's not going to make sense. Okay, so, and then I'm still left with a noun phrase left to expand. And now I have the cat eats. Okay, now what's noun phrase? A noun phrase is an AN. So this expands to AN. This actually seems tedious, and it is, and nobody writes Java programs this way. Every Java program you write can be derived from a start symbol using a left derivation, and it would take you thousands of steps to derive a complicated Java program. But what we're doing is we're learning the theory behind these grammars. So we're doing a real tedious little example to see how this stuff works. Okay, so now I've got 2 more derivations. I'm going to need 2 more derivations to finish my sentence. The cat eats. Okay, now I have to expand the A. A can be or the. I'm going to choose here. And I'm still left with one more symbol to expand. I'm still left with one more symbol to expand. Now I'm the cat eats and then I can pick what my N is these. So I'm going to cat eats a dog. Okay. Now I've got a sentence. The cat eats a dog. Okay. I've derived a sentence. Let me think. Okay, that sentence is not in this language. This is a grammar of a language, and this sentence isn't in that language. Okay, you wouldn't be able to derive this sentence because there is no article N. There's only the articles are A and the noun apple is not in this language. So even though this is an English language sentence, a cat eats an apple, it's not derivable from this grammar. So this grammar describes a certain piece of the English language. It's meant to be, give you a sense of how English works. Okay. So, but it's not. This is not a grammar for all of English. Okay. Now, what I just did is something called a left derivation. But here's another way I could also think about this. I can say that an S is the root of a tree, and an S has 3 branches to it. It's got a NP branch, a V branch, and another NP branch. This is another way of thinking about this idea of a grammar, that the derivation is another way of describing essentially a tree. I hope I can build this tree up. Okay, all right. So that was actually this first production. This first production essentially is saying I have a tree with this root and these branches. Okay. Now let's see. What's an NP? An NP is going to have 2 branches. A V doesn't have branches. And an NP here is going to have 2 branches. Okay? Okay. Kind of make the tree look nice. Okay. An NP has 2 branches, an A and an N. Okay. Now V doesn't have branches. V is either love, hates, or eats. I'm going to kind of extend this down. I'm going to make this one. Actually, maybe if I have room here, I'll make it eats. Almost don't have room to draw this properly. Okay, there's the eats. Okay, and then NP is going to branch. Let's see. Okay, spread that out a little bit. This is going to be an A and a N. Okay. Now, what's an A? An A doesn't have branches, and well, it's only got 1 branch. An N only has 1 branch. An A has 1 branch, and an N has 1 branch. And then what did I choose? I chose the A as, what did I choose it as? Was it the cat eats a dog? Okay, all right. So my little sentence, the cat eats the dog, has this thing here called a parse tree. Okay, this sentence has this derivation. So what I'm building here is the left derivation, and here it's the parse tree. Okay. And both of them give me the sentence, the cat eats a dog. Okay. The cat eats the dog parsed as a sentence was noun phrase, verb, noun phrase. The noun phrase was an article and a noun. The verb is eats, and the noun phrase is an article and a noun. And these are the choices I made. Okay, so these are so a grammar can be used 2 ways. It can be used in derivations or in parse trees. In the long run, we're going to be working with parse trees, and occasionally we'll be working with derivations. And it's just 2 ways of thinking about what this grammar can do for you. Now, what we usually do is we don't start with we don't usually start with a start symbol. We usually start with a sentence. So we might start with a sentence like the rat hates a dog, and ask, is that string, is this in this language over here? So the question is there a derivation that starts there and ends at the rat hates a dog. And there would you'd be able to start at S and make choices and end at the rat hates a dog. Or another way to think is, can you build a tree that starts with S, follows these rules, branches according to those rules, and down at the bottom, notice the bottom is the leaves. So you read the bottom as the cat eats a dog. As you read across the leaves of the parse tree, can you get that sentence? Now, if I made it, that wouldn't be in this language because there's no verb hits. So I would hit an obstacle. I would get to when I got to here and I wanted to expand verb, to get this sentence, I wouldn't be able to expand verb because the verb hits is not in this language. It's a trivial example, but it shows you that what the idea is that if somebody gives you a string, think of this as a string, is that string in this language that this grammar describes? Can you start with the start symbol, do a derivation, and end up with that string? Can you start with a start symbol and build a parse tree using these rules and end up with this string across the leaves? Okay, you wouldn't be able to parse so you wouldn't this string is not in that language. Okay, all right. So the ideas we have is a grammar, which is made up of productions. Each line is called a production. The top production is called the start production. The other productions can be in any order. Productions reference other productions and literals. And right now, we either concatenate things or we choose things. Later on, we'll see some other symbols. There's some other things you can do with grammars. This says whatever this expands to is followed by whatever this expands to. This says choose this one or this one. And this is a literal. Now, you could choose between productions. You could choose between literals. We'll look at some more complicated examples. Like this one, this is 3 productions in a row. This is 2 productions in a row, and this is 3 literals. A production can mix productions and literals, and it can mix concatenating with ors. So we'll see some examples as we go along, more complicated than that. So it doesn't have to be that a production is other productions or literals. You can mix them up. Okay. But the key question is, it's always going to be the same question. Somebody gives you a grammar, they give you a string, and the question is the string in the language described by the grammar? Can you derive the string or can you parse the string? Can you derive the string or can you parse the string? Usually we use the word parse when we build this tree, and we use the word derive when we write out the expansion step by step. By this guy expands to this guy, which expands to this, which expands to this. So when you think of starting with this and expanding over and over again, we think of that as derivation. Can you derive the sentence? If I say, build me a tree using these rules where the leaves of the tree are my sentence, that's called parsing. Can you parse? Programs parse. We'll write programs to parse into trees. Derivations aren't something you do in a programming language. So derivations are interesting, but we don't write code to do derivations. We will write code to create parse trees. We'll see that writing code to build a parse tree, you start with, the goal would be, our goal in the long run is to say, given this string, build this parse tree. Now, we could say, given this string, build this derivation, but that turns out not to be all that useful. I mean, there are programs that do those kind of things. Given a string and this grammar will produce the derivation. But from our point of view, in the case of programming languages, what's way more important is to say, given this string, build a parse tree. And we'll write code to do that. There are various there are algorithms that take strings and grammars and build parse trees, and those algorithms are called parsers. And it's a huge topic. 1,000-page books. There's all kinds of 1,000-page books on how to write a parser. A parser is a program that takes a grammar and a string and builds the parse tree for that string using that grammar. That's what a parser is. So it takes in a string and produces a data structure from it. Now, we've seen that already.
Lectureless parsing. What about lectureless parsing? I think that doesn't make trees.
Say again?
Lectureless parsing.
I'm not sure what you mean. All parsers build trees. That's actually the definition of a parser. A parser builds a parse tree. Okay, so there are things that sometimes you might call a parser that don't build a parse tree. There are ways of writing interpreters that can avoid building a parse tree, but then they're usually not called parsers. Okay, they're usually just like syntax-driven interpreters or something. But in the world of computer science, when you hear somebody talk about a parser, they mean something that from a string builds a tree. Okay. Now, the string usually won't be like this. Like, for example, in the case of the JavaScript language, or the case of Java. Let me go back and download this file here. Okay. Let me just show you. Here's a Java program. This is the string that needs to be parsed. Okay, what the contents of a file can literally be thought of as one long string. That's exactly how the Java language sees each Java file. It sees that as a string. Okay, and it needs to build the parse tree. The Java compiler, the first step in the Java compilation process is to take that string and build a parse tree for it. So the string won't be, in this case, the string isn't something in quotes, the string is something that's in a file. All the characters in that file are essentially one big long string. Okay. Yeah. And if you know this, like in the case of the Java language, none of this indentation really means anything. From the point of view of the parser, you can just, you can do this. You could delete all the insignificant white space. Like I cannot delete that. It needs to be there. I can delete that one. I can keep delete. The language doesn't, from the point of view of the language, this is just one long string. Now I'll show you. And this will compile. I'll do it for one method. Okay, so I took one of those methods and got rid of all the significant white space in it. Compile this. Compiler doesn't care. It's just one big long string. Yeah, it's just one. Literally, the compiler digests this file and turns it into one real long string in the compiler, and then starts parsing that string. And we'll learn a little bit about we'll look at some baby examples of writing parsers. We won't write a parser that can parse Java. Believe me, that's a tremendously complicated program. But we'll write baby parsers that can parse some simple languages. But the string for the Java parser is just the characters in the file. They make up one long string. Okay. All right. Now let's look at some other examples. In this guy, he's got another example of a grammar that we can play with. Here, this page here. It's like a homework exercise. Let's do the examples on this page here. Okay. Here's the grammar. It's actually one production. Okay. I'm gonna write it over here. Okay, I'm gonna actually. Okay, I'm gonna solve these we'll solve these problems. Windows is active. We'll solve these problems over here. First, let me write the grammar in a slightly different way. Everybody and his brother has their own way of writing grammars. There is not a 100% uniform way to write grammar. So let me give you a example. Here's a way of writing the grammar on the left. An expression is expression plus expression. Now here I'm going to use a name to represent a production. The literals, I'll put quotes around them, single quotes. Since I don't have a both, like here, the literals in a different font. I don't have a font over here. So I'll use quotes to mean literals. So an expression is expression plus expression. And I'll write or. So I'm continuing the same production here. Or it's expression times expression, or it's the literal left paren followed by the production expression followed by the literal right paren, or it's the letter A, or it's the letter B, or it's the letter C. Okay, so here's another way to write the grammar. I'm using this two equal signs to mean that the left-hand side expands to these right-hand side, but you either expand to this choice, which uses more productions, or you expand to this choice, or you expand to this choice, or you expand to just choice, this choice, or this choice. Okay, so here's one way to write it. Okay, now what I want to do is there's a page that just he has a page of problems. I've lost where I am in here. Practice. This is the page I want to be on. Practice. There's the grammar. Let's build parse trees for these expressions. Okay. So let's start with an expression and build a parse tree that gets us to A plus B. So now that would mean to get A plus B, we should obviously choose that. Oh, well, actually, let's do a derivation and a parse tree. So let's do it as a derivation first. Derivation for A plus B. Okay, expression becomes, well, to get A plus B, we'll do expression plus expression. Okay. And then we'll expand that as, well, expand the first expression as A plus expression, then expand the next exp as A plus B. So there was a very short derivation. Okay. And as a parse tree, that would be real simple. Expression would have 3 branches, a left branch, a center branch, and a right branch. Left branch, center branch, and right branch. So we're choosing this way of expanding. So this expands into a 3-branch tree. So that would be exp plus exp. Okay, now we choose exp as, well, on we choose this one for the left branch and this one for the right branch. So now this expands to just one thing. This expands to one thing, A, B. So there's the parse tree, A plus B. All right, so that was pretty straightforward. Okay, let's do another one. Do a derivation for A times B plus C. Okay. Okay, so we would take exp and derive it. Now this one we have to think a little bit. We want A times B plus C. Okay. And we look up here and notice that we actually can derive this one more than one way. We can actually do this one more than one way. We could, let's start with that. Let's take exp and derive it as exp plus exp. Okay. Now we're doing a left derivation, so that means we should expand this guy. What should we expand him to?
exp times exp.
Yeah, see, I need to pick, this plus here is going to have to be that guy. So this exp will be the C, so this exp has to be that essentially. So that means we're supposed to derive this to exp times exp plus exp. So since we're doing a left derivation, we know that we expanded this one. So the new stuff is what it expanded to. It expanded to this here. Okay. Now I do another left derivation. What should I expand him to?
A.
A. So A times exp plus exp. Do the next derivation. I've got the A times. Now I have to expand him. He expands into, well, he'll expand into the B plus exp. And then the last one is A times B plus C. So we expanded this one. Okay. But that's not the only derivation. We can do more than one derivation of this guy. And we'll see we can do more than one parse tree. So exp, well, okay, what should this guy expand to? Could expand to this one. Let's try, now there's no parentheses, so we don't expand to that. But can we do that? Let's do exp times exp. Can we make that work? Now, if we're doing a left derivation, we have to start with the first exp. Can we make this one work? What should this expand to now?
A.
Expands to A times exp. Okay. A time. Now, what should this exp expand to now?
exp plus exp.
Yeah, we should go to this. Now we go to this one And now this one expands into the exp plus exp. Okay. And then do a left derivation. So A times, now the next exp will expand to B plus exp. And then A times B plus C. Okay. Notice that we have two different derivations that can get from here to here. We say, technically we say that this is an ambiguous grammar. When a grammar when you can start from the start symbol here and get to your string in more than one way, so we're deriving that string. When you can derive the string more than one way, we say you have an ambiguous grammar. Okay, so this grammar is slightly ambiguous. Now, what about the parse trees? Let's see. So this guy, this derivation has a parse tree that goes along with it. exp will branch into two things. Well, I'm sorry, it'll branch into three. Okay. In this derivation, that branched into exp plus exp. Okay. Then the left exp in this derivation, the left exp did what? We're deriving this guy. What does this branch into? See, we're deriving this. So if I start off my tree like this, what does this one branch to? What's on the left of the plus sign?
exp times exp.
Yeah, so it's going to branch into three things again, but the three things are going to be it's going to branch into three. It's going to branch into exp times exp. On the other hand, what's this guy branch into?
C.
Just C. See what's this plus matches that one. So on this guy would branch to, oops, C. Okay. Now, then we can, now down here, this would branch just once, and this would branch just once. And this is going to be the A times B plus C. Okay, so there's the parse tree for this derivation. Now, what about the parse tree for the other derivation? Okay, let me do that down here. Let's do another parse tree. Okay, exp. Now we're going to do this derivation has a different parse tree for this same thing here. So exp is going to branch now into three things. Okay, but now to do this derivation, okay, so this branched into, I should say, exp something. What's the something now? In this other derivation, what's the operator here?
Multiplication.
Yeah, this would be the multiplication. See, the root expanded to expression times expression. So we can see, we read it from top down here, that the root expanded to expression plus expression. Okay. Okay. Now, this expression is just going to be the A. Okay. And then this one is going to branch into 3. Okay. This one will branch into 3. This one will be expression. This will be plus expression. Okay. And then this one will be the B, and this one will be the C. Okay. Notice I still have the same sentence, A times B plus C. If I read across the leaves, A times B plus C, A times B plus C. If I read across the leaves from left to right, that B is to the right of that times because it's on this branch of the EXP. So that's A times B plus C. Here's an interesting question. Does anybody see the difference between those two parse trees? What did they do to that arithmetic expression? It's an interesting question. This actually gets at the heart of what we're doing. Those two parse trees did something different to that arithmetic expression. Any idea?
It makes the tree looks inclined to the left or to the right.
Pardon me, say again?
Makes the tree looks inclined to the left or to the right.
I'm not sure you mean left or right of what?
Inclined. Trees. The trees look inclined, different.
Well, that's what the trees look like, but what is it doing to the arithmetic expression? Yeah, this tree looks different than that tree, but what does this tree say about the arithmetic expression that's different than what this tree says about the arithmetic expression? Try to think what this is telling us. This is saying what? The expression is a what versus the expression is a what?
A sum and a multiplication.
Okay, this expression is a sum of two things. This expression is a product of two things. But so what's that doing to this guy? Think trees. Oh yeah, somebody wrote it on the, yeah, speak up. I've said this before. The chat window is on a separate monitor off to the side of my desk, and I can't look at two monitors at once. Speak up. When you have a job interview, you're not going to do it by texting onto a text box. Get used to speaking up. Get used to saying things. You do not have technical interviews over a chat window. Please talk. Okay, yeah, order of operations. The two trees gave this expression different orders of operation. The top tree, what's it doing? The top one, the first derivation, it's doing what? Use order of operations idea. This tree does what?
It's doing the summation or the sum first.
No.
It
Because
does the
what's it doing the sum of?
Oh, it's doing the sum of the product because it
So-
starts from the bottom.
Yeah, so it's got to start from the lower part of the tree is what's being done first, because you've got to do that before you have an answer to the left-hand operation of, the left-hand thing of plus, well, you have to do this first. So this tree is actually the way we would think of this. The multiplication's done first. So this is the parse tree that's actually the right one from our point of view. What does this parse tree do? What's the order of operations in this second parse tree?
It does B plus C first.
Yeah, it does the addition first and then takes that sum and multiplies it. That's essentially as if you put parentheses around here. This is actually the wrong parse tree from our point of view. But from the point of view of this grammar, they're both correct parse trees. And one of the things we're going to learn is there's something wrong with this grammar because it did not distinguish between two parse trees. It gave us two parse trees. One of them we think is the right one. One of them we think is the wrong one. But from the point of view of the grammar, they're both right. We're going to learn how to write this grammar in a better way later on. This is some of the tricky stuff we have to do. That's actually the next chapter of the book, where syntax meets semantics. What is the semantics of that you learned in grade school? What's that thing mean? Semantics is the fancy way of saying, what does it mean? What is the meaning of A times B plus C?
Do the multiplication first.
Yeah, it means do the multiplication. That's the proper order of operations. The proper meaning of that is do the multiplication first. Well, this parse tree captured that meaning. So it's the right parse tree. This parse tree did not capture that meaning. But notice how the meaning of this expression can show up in a parse tree. That's the point of the second chapter of the book, where the title of the chapter is where syntax meets semantics. Okay, your grammars are kind of closely related to the meaning of your expressions. The syntax and the semantics can be intertwined in a certain way. And we see that here. This parse tree is the right meaning. This parse tree is the wrong meaning. But from our point of view, the problem is really with our grammar. The grammar is not written well. We're going to make this grammar written in a more complicated way. And then with a more complicated way of writing this grammar, there'll be one way to parse this, and it'll be the right way. And we won't get this extra parse that we think of as the wrong way. Okay. All right. So there was more than one way to parse this guy. Now let's do another one. Let's do the last one. So the string is A plus left parentheses, B close parentheses. Okay. Oh, what did I do? Okay, that's the string. Okay, so let's first do a derivation of it. EXP should expand to, okay, if we're going to do this one, what do we expand EXP into? Okay, the grammar's over here. Let's see, I'll scrunch these over. Okay, so what should we expand EXP into? We've got 5 choices. This one, this one, this one, this one, this one, or this one. If we're going to derive this guy, what should we expand first?
It would be the expression in parentheses.
Yeah, we need to do that first. Okay. Now, there's only one thing to expand in there. So now the question is, what should he expand into? What would that one expand into now?
I think it's expression plus expression.
Yeah, we've now accounted for that thing in the term. You see, we've accounted for that and that. So what we're trying to parse is what's left inside of there. If you look at A plus parentheses B, well, it's not, it doesn't look like, it doesn't have parentheses around it. It doesn't have a star in it. It's not A, B, or C by itself, so it must be expression plus expression. Okay, now we're doing a left derivation. So now we have to expand this guy. What should he expand to?
A.
A. Okay, so he expands to A plus exp, close parentheses. Okay, now there's only one thing to there's only one choice of what to expand now. We have A plus. What should this one expand to now?
The parentheses.
Yeah, the
Expression?
parentheses. See, there is the left paren A plus. We've accounted for the left paren A plus, and we've accounted for this closed paren at the end. What we're doing is we're parsing the parens, we're parsing that part now. This guy is that part there, which means we're doing parentheses, exp, close parentheses, close parentheses. So this one expanded into that. Into that. All right. Now one got another symbol to expand. So now we got A plus left paren. What can this guy expand to?
B.
B. So that expands to B. We're done. Okay. So there was the derivation of that expression. Okay. Then if we want, we can do a parse tree. So the parse tree is going to be an exp. Now the parse tree is going to look a little bit different. It's got 3 branches. Okay. The root expanded to this. So it's got a left paren on the left. This is an exp, and we've got a right paren over here. Then the exp expands to 3 things. Okay. This one expanded to exp plus exp. Okay. This one just is the A. And then this one expanded to 3 things again. Okay. It expanded to left paren, exp, right paren, and then the exp expanded to the B. So there's the parse tree. Okay. Notice if you read the leaves from left to right, it's going to say left paren of A plus left paren of B, close paren, close paren. See, that was this guy here. See, you read the leaves from left to right, but you have to make sure you realize that this A is not to the left. See, if you look at the way the tree, yeah, if you look, this A is actually to the, it's right below that left parentheses, but it's really to the right of it because it's in this tree here. So everything in this tree is to the left of that parentheses, and everything in this tree, everything in this tree is to the right of that parentheses, and everything in this tree is to the left of that parentheses. So this is the leftmost symbol, and inside of it is this tree here. Then the leftmost symbol of this tree is the A, so the A is next to the left parentheses. Okay, so there's the parse tree for that one. Now notice that this one didn't have more than one parse. This thing could only be parsed one way, but this is the one that could be parsed two ways. Okay, the grammar has got an ambiguity over the addition and the multiplication. See, it's got an ambiguity over here. The parentheses group. So, but the plus and the multiply, this grammar doesn't have precedence built into it. This grammar doesn't say that multiplication has precedence over addition. And that's one of the things in chapter 2, we're going to learn how to do that. How would we write the grammar in a way that says multiplication has higher order of precedence than addition does? So we have to write the grammar in a better way to force this guy to be done before that one, so that this thing would have only one parse. Okay, so we've done a lot of practicing. So we notice that we're practicing using a grammar to find derivations for strings. So somebody gives us a string, and we say, okay, we can derive the string. Someone gives us a string, and we can derive the string or parse the string. So you can derive it or parse it. You can derive it. You can derive it or you can parse it. Okay. All right. Now let's look at, let's see. Over here, I put a bunch of links here to some kind of famous grammars, okay, that are pretty useful. So for example, let's look at this middle one, URLs. Okay, a URL is what you put up here in the address bar of a browser. That's a URL, okay? That's where you type something that tells the browser where to find a web page, okay? What is the syntax of URLs? What can be typed up here? For example, it's legitimate for me up here to put a colon and an 80 there. See, that worked. Yeah. Notice it did. I didn't get any error. It went. The browser removed it, but it's legitimate for me to type colon 80. Okay. Now it's also legitimate for me to type colon 100. And if you notice, it didn't connect. There is no, actually, this didn't work right. There is no math.pnw.:100. This thing didn't load properly. Let's see. Oh, see there, finally. It took a long time for it to say. See, that didn't work. That is legitimate for me to write that. That's not an error, but there is no machine. This is called the port number. So this is called the host, and this is called the port number. The syntax of URLs lets you write host colon port number, but you might type the wrong port number. The default port number is 80. So when you type in 80 there, that's the default port number. So that works. Okay, and it actually disappears from the URL. Okay, what are the other things you can type into URLs? What is the syntax of what's allowed in a URL? Okay, so for example, see that little tilde character? That little tilde character is allowed, but there are other characters that aren't allowed. So for example, if you type, well, let's see. Yeah, I'm trying to do a grammar error. Usually if you do a grammar error in a URL, you don't get a syntax error message. The browser just says it can't load the page. Okay. Well, okay, let's go over here. Here is the grammar for a URL. The way you read this is that here's the start symbol. And this is not written real well, but a URL is either generic HTTP address, FTP address, news address. So these are the choices. Now, some of these link to what they are. The person who created this page is kind of weird. Like, see, HTTP address links to this thing here. So if I click on that, see that one went to the top of the page. And FTP address links to this one here. But they didn't link this one to this one. Okay. So now HTTP address is what we're working with. We are working up here with the HTTP addresses. What's an HTTP address? An HTTP address, now the way you read this is, see, they're using a syntax where this is the left-hand side and this is the right-hand side of a production. Over here, the left-hand side and the right-hand side were just written in line with a symbol between them. Over here, we wrote the left-hand side and the right-hand side with a symbol between them. But a lot of people like to write their grammars with the left-hand side on one line and what it expands to on a different line. Okay. So what is an HTTP address? It's the letters HTTP : / followed by host port, followed by, now the way you read this is the square bracket means an optional / path, followed by an optional question mark with the question mark means a search term, and then a string that's a search. Okay, so what you can type in this address bar is the letters HTTP : / then host port. Host port, let's look for it. The way I like to do this is if you copy, then Control F, see, now you can see where all the word host ports are. Here's what host port is. Host port is host followed by optional : port. Well, what's a host? A host is either a host name or a host number. Okay. What's a host name? A host name is a I alpha with an optional dot host name. Okay, that's kind of weird. Notice that we finally got one that's recursive. A host name is an I alpha. What's an I alpha? You keep looking down here. There's an I alpha. An I alpha is an alpha followed by an optional X alphas. Okay, what's X alphas? Okay, notice this is as you'll see, this is what grammars look like. It's just a chain of definitions. Here's what they're doing here. An I alpha is an alpha. Well, an alpha is the letters of the alphabet. Okay, alpha means a letter from the alphabet. So an I alpha is an alpha followed by an optional X alphas. Notice that this is plural. Okay. X alphas. Okay, X alphas is an X alpha. Remember, alpha was the letters of the alphabet. Okay. An X alpha is an extended alpha. It's an alpha or a digit or a safe or an extra or escape. An X alpha is an alpha, so it's a letter. Does anybody see the trick of what they're doing here? They want to eventually say it's a name. Think of it, in almost every programming language you know of, what's the rule for the syntax of a name? Is that a value variable name?
Yes.
Is that a valid variable name?
Yes.
Is that a valid variable name?
No,
Why not?
because it starts with a number.
Okay, so you're not allowed to start a variable name with a number, but after you start the variable name with a letter, you can put numbers anywhere you want, right?
Right.
That's what they're saying here. What is a host? A host is a host name. Host name is an I alpha. Okay, I alpha means essentially a name. Okay, then you look here, and what they're basically trying to do is say that you can start with a letter, then after the letter you can use extended alphas. So initially you have to start with a letter, but then after the letter you can follow X alphas. X alphas are letters, digits, and a few safe characters. They use the word safe. Well, what's safe mean? These are the characters you can put in a name in a URL. $, hyphen, underscore, @ symbol, period, and ampersand. Notice you can't put a plus in a host name. You can put a $sign in a host name, a hyphen, and an underscore, and an @ sign. I think that's a period. No, that's a comma, and an ampersand, but you can't put a plus sign. So a host name has to begin with a letter. It has to begin with a letter. But then after the initial letter, you can have either letters, numbers, or what they call safe symbols. You can have letters, numbers, safe symbols. But the only safe symbols are these guys. Okay? But then they say you can have an extra symbol. But then there's some more symbols that they call extra. Notice that safe and extra aren't the same thing. So for them, these are safe letters that can be used in some places, and these are extra letters that can be used in other places. In a host name, they let you use both safe and extra, but in other places, they may only allow safe letters. In other places, they may allow the extra letters. Okay, now notice that even here, the plus sign's neither safe nor extra. Notice that the plus symbol is neither a safe letter nor an extra letter. You can't put a plus sign in, but here's where plus sign, there's something called XP alpha. If they allow an XP alpha, they're allowing an X alpha with a plus sign thrown in. See how the grammar spells out all these rules. Grammars are ways of spelling out all the rules, in this case, the rules of what you can put up here. What is allowed up here in a title bar, in the address bar. This rule is determined by the W3 organization, which is the organization that runs the standards of the internet. These people, essentially, they set the rules for the internet. Okay, it's an international organization that sets rules for the internet. And one of the rules that they set is what can you put in an address bar. So they have this grammar. They give you a grammar for what you can type in a URL. This is typical real programming. When I want to tell you what you can type, I give you a grammar. Well, we'll run out of time, but for example, here's a grammar for Java. It's pretty long. There's a grammar for everything you can write in the Java language. That describes everything you can write in the Java language. They use the syntax that there's the thing you expand. It expands into those things. This expands into those things. Yeah. So they write it kind of the same. Instead of writing, this is the thing that expands into those things. Okay. And everybody's got their own slightly different notation for describing grammars, but there's the grammar for, and then here's the grammar for JavaScript, and it's really complicated. Surprisingly enough, it's, if you click on that link, be very patient. Be real patient. It takes, see, that page is 1,000 pages long. That web page, this is a 1,000 page web page that describes the grammar for JavaScript. It's 1,000 pages long. It's weird that they would do it this way, but this is a 1,000 page web page. If you print it, it would print to 1,000 pieces of paper. So it takes a long time for it to load, but this is the grammar for JavaScript. Okay. So these are, yeah, and so we'll learn how to read these. We'll on Thursday we'll do some more examples of reading these grammars and seeing how get kind of some practice in the idea of reading grammars. And for example, this one's real cool because it shows you the grammar for all of SQL. Like, what does a select statement look like in SQL? But this is a grammar written in what's called train track diagrams. But it tells you the language of SQL. Okay, so we run out of time, so we're going to quit there. But so on Thursday, we'll look at more examples of grammars and how they can be useful. Anybody got a last minute question? Anybody got a last second question? So read the next chapter. The next chapter in the book is this chapter 3. Like I said a minute ago, this is where you taught how do you give multiplication precedence over addition. You have to do that by writing the syntax of the grammar in a way so that the grammar says your proper semantics. So that's a kind of a tricky thing. So that's what we'll start talking about that Thursday, and it'll also take us through next week. So that's something we'll spend a little bit of time on. That's a real important chapter. Okay, so read chapter 3. It's not easy. There's some pretty deep stuff in that chapter. Some pretty non-trivial ideas in there. Okay, so I'll go ahead and stop sharing, and we'll meet again on Thursday. Oh, and I have office hours this afternoon. And if you have questions about the homework assignment or if anything, you can come to office hours or send me an email. Okay, so I'll stop, and we'll meet again on Thursday. Bye.